In January 2005, NASA launched a unique probe into space. Its mission was to find out where water on Earth originally came from. Called Deep Impact, this probe traveled 270 million kilometers to reach a comet. Within this comet were hidden secrets that scientists had been searching for centuries. The entire universe, there is only one place where human beings can live: Earth. It seems as if Earth was specifically designed for humans. It contains all the elements essential for life: water, food, and oxygen. In this vast and interconnected universe, there may or may not be another planet where life can exist. But for now, Earth is the only place we know of where humans can survive unaided. However, 5 billion years ago, Earth did not even exist. The spot where Earth and our solar system are now located was once on the edge of the Milky Way galaxy. Before our planet formed, this area was home to a massive cloud filled with dust and gases. Eventually, something happened within this cloud that transformed it into the planet we now live on. This cloud of dust and gases is known as a molecular cloud, composed of dust particles including sand, silicon, and traces of various metals. The formation of this cloud was influenced by the remains of dead stars. In the early universe, stars that had burned through all their fuel exploded, scattering their particles across nearby regions in space. This cloud did not look like the clouds we see in the sky. Instead, it appeared much different and was captured with the help of the Hubble Space Telescope. Astonishingly, this cloud was about 100 light-years across, meaning that if light started traveling from one end, it would take 100 years to reach the other. To put it in simpler terms, this dust cloud was 6 million times the distance between the Sun and Earth. This was the cloud from which new stars and planets would eventually form. The force that shaped this cloud, turning it into stars and planets, was gravity. Yes, gravity. The same force that doesn't exist in space as we experience it on Earth, but instead is generated between objects. Two objects in space attract each other due to their own gravitational pull. The object with more mass has a stronger gravitational pull. In the molecular cloud, particles began to attract each other due to this gravity, causing larger particles to clump together. The larger particles in this cloud began to attract the smaller particles, causing them to collide rapidly. These collisions generated energy, which heated up the core at the center of the rotating cloud. This process continued for millions of years, with the core of the molecular cloud growing larger, spinning faster, and becoming increasingly hotter. Eventually, this core transformed into a massive fireball, which became our Sun. The remaining molecular cloud started orbiting around this newly formed Sun. The particles within this molecular cloud eventually formed the planets of our solar system, including the moons orbiting these planets, and even created conditions for life. But how exactly this happened remained a mystery, until now. The idea that a molecular cloud could form a star such as the Sun was first proposed as a hypothesis in the 1700s by German philosopher Immanuel Kant and French scholar Pierre-Simon Laplace. At that time, it was merely an idea. However, between the 1920s and 1950s, as telescopes became more advanced, astronomers observed numerous dust clouds in space with their own eyes in which new stars were being born. Still, observing the interiors of these clouds in detail was not possible even with telescopes. Then, in the 1970s and 1980s, the invention of radio and infrared telescopes solved this problem as well. Now, it became possible to look inside these clouds of dust and gas. Astronomers used infrared telescopes to observe new stars forming within molecular clouds, proving that stars are indeed born inside these clouds. Later, the leftover particles from the cloud form planets. But how does this process start? Initially, various ideas were floated, but in March 2003, an experiment on the International Space Station provided an answer to this centuries-old question. The astronauts on the ISS decided to observe how different materials behave in space. They created water bubbles, added dissolvable tablets inside them, and spun a plastic bag filled with salt to see how it would behave. Although these experiments were intended for other purposes, Their final experiment unexpectedly answered this ancient question. When salt was placed in the plastic bag after a short time, the salt particles began sticking together. This happened because in space, these particles attract each other due to gravitational forces. The key takeaway is that within a molecular cloud, tiny particles of dust and gas start attracting each other, sticking together and rotating around the sun in the same direction. This is the fundamental process through which planets and other celestial bodies begin to form. Just like the salt particles in the experiment, these particles in the molecular cloud began sticking together, marking the beginning of planet formation. Around 4.5 billion years ago, particles in the molecular cloud started clustering in the same way as the salt particles in astronaut Don Pettit's experiment on the ISS. As this cluster of particles grew to about 1 kilometer in size, the size of a mountain, it developed enough gravitational pull to attract even more surrounding particles, much like a vacuum cleaner drawing in dust. This process continued for the next 3 million years, and eventually, 20 protoplanets emerged, all orbiting around the Sun. These 20 bodies had become significantly large by this point. Due to this, the gravitational forces of these growing protoplanets began to attract each other during their collisions. Eventually, they started to collide, and with each impact, two planets would merge to form a larger one. Over time, as the collisions continued, the number of planets in the solar system, which had originally been around 20, gradually decreased to only a few. Among these, Venus, Mercury, Mars, and our Earth remained. However, Earth at that time was not the blue, life-filled planet we know today. Due to these constant collisions, it was extremely hot, resembling a giant fireball. Astronomers believe that it took about 30 million years for Earth to reach its current state, a cooler and more stable environment conducive to life. At that time, Earth's temperature was close to 5,000 degrees Celsius. This meant that if any living organism had existed on Earth, it would have evaporated in less than a second. Life on Earth would only become possible once the temperature dropped. However, as it cooled, Earth still faced a major threat to its existence: solar storms. Yes, the radiation emitted by the sun when it reaches a planet can severely damage its atmosphere. These solar storms affect other planets as well, making it difficult for life to thrive. It was only once Earth's atmosphere began to stabilize and shield itself from these solar storms that the conditions for life started to improve. There is no need to look far. Mars, Earth's neighboring planet, is a clear example of how solar storms destroy the chances for life. However, Earth managed to protect itself from these solar storms, and the secret to this defense lies within Earth's core. As Earth began to form from the molecular cloud, its temperature increased significantly. This extreme heat transformed Earth into a giant fireball, causing the rocks to melt. The molten materials contained iron and nickel, which are quite heavy. Due to their weight, the iron and nickel sank towards the center of the Earth, forming its core. This process played a critical role in creating a magnetic field around Earth, which helps protect the planet from harmful solar radiation and solar storms, making life possible. Geophysicists believe that whenever molten iron is spun, it generates a magnetic field around it. Since Earth contains a large quantity of molten iron in its core, this process generates a strong magnetic field. The influence of this magnetic field extends into space, and this region is known as the magnetosphere. Normally, Earth's magnetic field stretches about 370,000 kilometers on the side facing the Sun, roughly the same distance as the Moon. On the opposite side, where Earth is not facing the Sun, the magnetic field extends even farther, reaching millions of kilometers into space. This magnetic field is what protects Earth by deflecting harmful radiation from the Sun, preventing it from reaching the planet's surface and allowing life to thrive. At the North and South poles, the magnetic field is weaker, which allows some solar radiation to enter Earth's atmosphere. When this radiation interacts with particles in the atmosphere, it produces the aurora effect, also known as the northern and southern lights. However, the radiation here is so minimal that it doesn't pose any harm to life. Earth, which had already survived solar storms, was still not perfect for life. It had to go through one more difficult phase, a planet collision. But how do we, as humans, know about this? To find the answer, we have to look back to the year 1960. The United States planned several Apollo missions and sent astronauts to the moon for research purposes. It was initially believed that the moon was a chunk of Earth that somehow broke off. However, when astronauts traveled to the moon and brought back rock samples, scientists noticed something unexpected. These rocks did not resemble the ones found on Earth. They appeared to have been burned or heated in some way. Further investigation revealed that the oxygen isotopes in the moon rocks were identical to those found in Earth rocks. This discovery provided evidence that the moon was once part of Earth. However, intense heat, likely from a catastrophic event, caused the separation, leading to the moon's current state. Such intense heat could only be caused by a massive collision, and that's exactly what happened. While Earth was gradually cooling, another planet, about the size of Mars, was moving towards it. This planet was named Theia. When Theia collided with Earth, an enormous amount of energy was released. The impact sent fragments of both Earth and Theia scattering into space. These pieces eventually began to orbit Earth, and over time, they coalesced to form the moon. This catastrophic collision not only gave rise to our moon, but also played a key role in shaping the Earth's current composition and conditions. The fragments that orbited Earth continued to collide and merge over thousands of years, much like the particles in the molecular cloud. This process eventually led to the formation of the moon. Initially, the moon was much closer to Earth. Experts believe that the moon appeared 15 times larger in the sky than it does today. However, over time it has been slowly drifting away from Earth at a rate of about 1.5 inches, approximately 3.8 centimeters, per year. This gradual separation continues to this day. It's important to note that the catastrophic collision between Earth and Theia, which led to the formation of the moon, were two crucial events that made our existence possible. Scientists believe that without these events, life might never have formed on Earth. But how did this happen? When a planet the size of Mars collided with Earth, it caused a significant tilt in Earth's axis. Before the impact, Earth was rotating on its axis without much tilt. This collision shifted Earth's axis slightly, giving it the tilt we see today. This tilt is responsible for the planet's seasons, creating a more stable environment that allowed life to evolve. Without this tilt, the climate on Earth would have been much more extreme, making it less hospitable for life as we know it. Earth's tilt of 23.5 degrees is what gives rise to the different seasons we experience. As you know, one full rotation of Earth represents a day, and one complete orbit around the Sun makes up a year. Because Earth is tilted, the northern hemisphere is closer to the Sun during certain months, resulting in the summer season. In contrast, during winter, the northern hemisphere tilts away from the Sun and experiences colder temperatures. This axial tilt ensures that Earth's surface does not receive the same amount of warmth or cold year-round. As a result, we experience varying temperatures leading to the change of seasons. These changing seasons are why we have different fruits and vegetables available throughout the year, depending on the climate conditions in each season. Throughout the year, we observe different colors in nature due to the changing seasons, and the monsoon rain cycle provides us with clean drinking water through rivers. Additionally, the moon's formation plays a significant role in generating ocean waves. These waves provide essential nutrients to marine life. Without these waves, nutrients in the ocean would remain concentrated in just a few spots, limiting marine life. But this raises an important question. Ocean waves are formed because Earth has water, which is crucial for life. So, where did Earth's water come from in the first place? Scientists believe that Earth's water likely came from two main sources. First, water-rich asteroids and comets may have collided with Earth in the early stages of the planet's formation, bringing water to the surface. Second, volcanic activity on early Earth could have released water vapor, which condensed to form oceans over time. These two processes likely played a significant role in providing Earth with the water needed to sustain life. The origin of Earth's water has been one of the biggest mysteries for the scientific community. In January 2005, NASA launched a probe called Deep Impact into space, aiming to explore this mystery. The probe was sent on a journey of 270 million kilometers to study a comet named Tempel 1. Attached to the probe was a copper impactor weighing about 350 kilograms, designed to collide with the comet. On July 4, 2005, this impactor struck Tempel 1 at a speed of 37,000 kilometers per hour, creating a massive crater. The goal of this mission was to better understand the composition of comets and, by extension, the possible origins of water on Earth, as comets may have played a key role in delivering water to our planet. The impact was captured by the Deep Impact team using radio telescopes, and what they observed was truly astonishing. The light emitted from the collision was analyzed using spectroscopy, revealing that Tempel 1 contained water in the form of ice. This confirmed that comets, located far from the Sun in the asteroid belt, have water inside them. But the question remained, how did these comets containing water leave their orbits and travel all the way to Earth, and that too in such large numbers? Experts believe that this process could have been triggered by the largest planet in our solar system, Jupiter. Jupiter, with its immense gravity, is thought to have been responsible for redirecting these comets toward the inner solar system, where they collided with Earth, potentially delivering significant amounts of water to our planet. This planetary interaction is likely how water was brought to Earth in the early stages of its formation. Yes, Jupiter, the largest planet in our solar system, has a gravity many times stronger than Earth's. Its position is crucial because it orbits close to the asteroid belt. Scientists believe that, in the past, Jupiter's massive gravity could have disrupted the normal orbits of large comets and asteroids within the asteroid belt. Normally, objects in the asteroid belt follow a circular orbit around the Sun. However, Jupiter's gravity would have attracted these objects, altering their paths. Instead of moving in perfect circular orbits, they would have shifted into elliptical orbits, oval-shaped paths, making them more likely to be drawn closer to the inner solar system, including Earth's path. When these objects crossed Earth's orbit, the gravitational pull of the planet could have pulled them in, sending them crashing into Earth and potentially delivering water in the form of icy comets. This is how Jupiter's gravitational influence could have played a key role in bringing water to Earth. Geologists believe that water did not originally exist on Earth, but arrived around 500 million years after the planet's formation. How do we know this? The answer lies in zircon, a mineral found in rocks. Zircon forms in the presence of water, and because it contains uranium, it allows scientists to use radiometric dating to determine its age. When scientists analyzed zircon samples found on Earth, they discovered that these minerals were about 4 billion years old, meaning they formed roughly 500 million years after Earth's creation. This provides strong evidence that water was present on Earth by this time. This timeline fits with other events in Earth's history, such as the formation of the planet from the molecular cloud, the collision with a Mars-sized planet, Theia, the tilt of the Earth, and the creation of the Moon, which all contributed to the conditions that allowed water to accumulate and form oceans on Earth. In summary, these processes, along with the evidence from zircon, suggest that Earth's water came later, after several significant planetary events, which made Earth capable of supporting life. Due to Jupiter being millions of kilometers away, the water on the Earth seems to be improving. So now you tell me in the comment section how oxygen came in the atmosphere of the Earth. Hope you guys will also like and share this video. Thank you very much for your kind comments. See you in the next video. Cheers.